Almost, I hear. Well, it's a very good sign that you're still talking because it means that you are connected. So, if you want to know more about MS2LDA, then it may be nice, maybe better to also listen a little bit to me. If not, feel free to do other things. So first of all, we heard about MS2Query and MS2Mesh this morning, and we showed examples of how to use it on the example data. If you want to try it out in your group data, that's possible. However, please use the notebook in the solutions folder because there's an additional step needed to match all the feature IDs between your data, the group data, and the results of MS2Query. So otherwise, I will get an error. We try to fix it. Let us know if it doesn't work yet, and Florian is around. You're around till tomorrow. All right. Another question I have. So I put in the GitHub a lot of information and links out the various data for the groups and the example data. However, you've seen yesterday, the day before yesterday, or yesterday, how easy it is to build a server. If you all try, with like 50 or 60 people to start a job, well, I can tell you the MS2LDA web server is way less fancy than the super cluster in San Diego. So it doesn't take a lot of you to kill it. So my kind request is to not all go there now, because then everything will freeze and even a live demo will not work. All right, so just listen to me. I will show you a few things, and then at your own time, at your own tempo, you can go there, and the server can also hopefully handle all your kind requests then. All right. So if you know me a little bit, you know that I like to take pictures of various things, including the sky. And this is a sunset right in front of my window in Wageningen. And actually, I wanted to use it as a start into the lecture on MS2LDA. And yeah, so basically, I made a highlight. Still working? Yeah. So I made a picture, a live of a picture. And my question to you is, what do you see? And there's no wrong answer. That is the nice thing, right?
Clouds.
Clouds. Okay. Good. Eagle. All right. I didn't see the eagle yet. Good. More.
Hippo.
And hippo. Yeah. All right. Not sure what Robin had for the coffee break. Coffee. All right. So what I saw was a man with a moustache, with 2 eyes, and a nose, and a huge moustache. Yeah. So now you all see it probably. All right. But this is like pattern recognition, right? Our humans with our eyes, we are really good at pattern recognition. Well, you have doubts, but I bet you can see the difference between a lion and a bird, let's say, and then assess whether or not you have to run away. Yeah, that's what they say where it came from. Anyway, pattern recognition is actually also what MS2LDA is doing, but obviously not with our eyes, but then using a computer. And well, we have to move here to make it work. Yeah. So this is another picture, and I think some of you already know, I've been here during my studies. I did my internship in Copenhagen. So I lived here, and this was the opposite of the street where I lived, in the Nuremberg. And yeah, basically, I'm going to ask you again, what do you see? Window?
Face. Faces.
Faces? Okay.
Windows.
Apartments. All right. I was actually looking for a very simple answer, right? And why is that? Well, because everywhere in the world, yeah, we will recognize it. Why? Because there's windows, there's some structures to it that we all recognize as houses, right? So so actually, we're using some common concepts with humans to build apartments. And the analogy with nature is nature also uses common things, common chemistry, common biochemistry, substructures to build up molecules. And the idea is then, of course, how can we extract them from the data? In some cases, we can recognize them quite clearly. And in other cases, like I just showed, it's less clear what it actually is, and we will need to do our best to annotate. So I will not ask you again, but this is a picture that some of you may recognize from earlier talks. And this is a picture I took near San Diego. And with our eyes, we can clearly see there are two groups, the seals and the birds. And the idea is that can we not use our eyes, but use the computer to do the same with them with the spectra, recognize the grouping that is implicitly there, propagate that information, and annotate these chemistries. And we've seen examples of how molecular networking is doing that. And now we're going to discuss substructure discovery. And I already showed you the analogy between spectra and text. If you remember the example of coffee and cookies and cake and cappuccino from earlier today. And also MS2LDA uses that analogy. So we have different parts of the text here with different words, different colors. And each color represents a group of words that is often co-occurring, let's say in a large body of text. You have to imagine we have like thousands of documents. And then the algorithm, the LDA algorithm, tries to look for what is commonly always co-occurring. And in red, we see words like plate and united, professional, etc. And in blue, we see words like funding and predators. And in green, renewable energy, etc. So the analogy with the spectra is that each word becomes a peak or a neutral lot, and each text document becomes a spectrum. And you can imagine in our data of during this week, with more than 6,000 spectra. So 6,000 of those things with all these peaks, and then the algorithm will try to find groups of commonly co-occurring peaks. And the nice properties of the text mining, in this case the topic modeling, is that each text can contain one or more topics. So you can see the example here. Document 1 contains 2 groups of words, and document 2 as well. And if you think about molecules, they sometimes have only one substructure, but sometimes they have 2 or 3 or even more. So that is nice. And also we can see that the same topic can be present in 2 documents, right? Or even more. And if you think about substructures and molecules, of course, we see that. We see the same substructure used again and again and again, as I just told when we were discussing like the common building block of nature. So actually, we can actually use that to see if it also works on spectra. One thing I have to tell you is that the algorithm itself doesn't annotate anything, right? It just presents you with the groups and it says good luck. Also in the text. So in the text mining, you will need to assign the topics like football related, business related, etc. And alike in the metabolomics data, we will need to annotate. I'll get back to that. So I won't ask you the question anymore if it works, because the tool is around for a while, and luckily it seems to work quite nicely in many cases. I tried it out. I was in Scotland at the time, in Glasgow, during my postdoc, and I went to the shop and I bought some Scottish ales, and I took 10 ml for science, and the rest I tasted, and they were all pretty good, I can tell you. And then beer is nice because it contains a really complex mixture of 3 metabolomes, making it a very complex metabolomics mixture. And we can see how MS2LDA could extract several biochemical relevant building blocks. So here you see the structures of those building blocks and not the patterns themselves. And you can see examples of amino acid related substructures, some aromatic ones, some purine related. So there's a whole bunch of different chemical compound classes already represented here. And here we see some example, because I thought that's also nice to go a bit more in depth. So we see an example of 2 fragmentation spectra that MS2A grouped into one motif or master motif. And we can see that all the peaks in blue in this figure, they are belonging to the motif, and all the other peaks not. And here we can see that there's quite a few intense peaks that MS2A grouped as always being together or quite often being together. And with my own background in natural product chemistry, tomato, I am a tea and tomato in Wageningen doing my PhD. I could immediately see, that is ferulic acid related. So I went on and looked in literature if that made sense to see that in beer. And yeah, it could well be. So then I could annotate this particular master motif as ferulic acid related. And we could actually detect it in only 11 out of the 1,000 spectra. Why I'm saying this is that, you know, you get a sense of how specific or sensitive a motif is or can be. And for the paper, we also validated the tool with standards. I think we've seen some validation before when I discussed briefly MS2 query. So, and this is maybe also a nice moment to say that back then we had access to 5,000 spectra from DMPS and 2,000 from MassBank. And nowadays there's more than 500,000 spectra in DMPS, and the MassBank numbers I don't know by heart. So you can see that in the last 7 years, the amount of available spectra has been increased by a factor of 100. So by the way, it's spectra that I'm saying and not unique molecules. I think we are now at 23,000 unique molecules in GMPS, and I'm looking at all of you to increase that, okay, to more. Then using the 5,000 molecules from GMPS, we started to validate it. So we run the tool, and then I assessed all the motifs that came out, all the patterns. And as we can see here, these are 3 molecules, because it's a fragmentation library, so we know the structures and the spectra. And I think by now you have probably seen the common denominator in the 3 molecules. But you also see that the spectra are not that much alike, I think. They do share common features, but they're clearly not the same. And that is also something that is nice when you use MS2LDA. I mean, it doesn't need to be exactly the same pattern. It does allow for some fluctuation and flexibility in there. So it's this adenine part that is common if you haven't seen it yet, and it's the red peaks that kind of are representative for it. And actually, this is also the first master motif that I saw with one of the first results that we got from the first attempt with Simon Rogers and Joe Wandy back in 2015. And it was also from a beer file. And then I spotted this adenine related master motif, and then I thought, okay, could work. And then it still took like 2 years to get it to really work like it is now. But at least it is one of the first motifs that I could immediately by eye validate. And the nice thing is we have multiple motifs per spectrum. So we have a green loss here, and that is actually connected to the sugar bit of adenosine in the middle. So that molecule, adenosine, is actually completely decomposed by MS2LDA in 2 substructures. And you can also see that part can also be found in other molecules. So connecting molecules in different ways. So a few years after the publication in PNAS on the topic modeling approach with Joe Wandy, we built this MS2LDA.org, where I kindly ask you still not to go, all of you at the same time. But it was originally aimed to run MS2LDA on your LCMS file and then also be able to look at the results. Nowadays, I think what I would do is first run your thing in GMPS, then run GMPS MS2LDA, then download the dictionary file. And if you want to know more about specific motifs, you can go to MS2LDA.org, upload your dictionary file, and then browse the motifs further. And then you will get an overview of your experiment with various options that I will briefly also highlight at the end of the lecture. but to get a little bit of an idea, so you can browse through the different motifs. Each motif is a spectral pattern found by MS2LDA. And you can actually also annotate these motifs yourself. So you can see that in some cases you see text on the screen. That is why I added an annotation to a particular motif. And also you can go to the more details of the motifs, which peaks, which fragments, which losses were found to commonly occur. At the end of the lecture, I will dive a little bit further into that, but then at least you got an idea now. And another thing is that you can visualize the results. And you've seen molecular networks where we have nodes and edges, nodes representing spectra or features, edges representing similarity, cosine score, modifying cosine score, if above a certain threshold. But here we have, interestingly, we have master motifs and we have molecules and we have edges. So actually, this is not the network, a network like you've seen before. There's a bipartite network where we have one group of motifs, the big or smaller circles, red, orange, and we have the squares, which are all the spectra. And that is connected when a spectrum is linked to a motif. And what we can already see is that in some cases, some spectra are connected to several motifs, 2 or even more. And in other cases, they're only connected to 1. So this visualization could help in trying to get an idea what are the really generic motifs found across many spectra, which ones are found in 2, which spectra are found in 2 motifs, etc., etc. In other words, it represents an alternative way of looking at the data. So then moving on in time, we also combined MS2LDA with in silico annotation tools, such as Magma. And we took the data from the standards. So we know spectrum and we know structure. And we said, okay, with Lars Ridder, okay, we worked on this to integrate this and to get to some sort of automated annotation when we know the structure and the spectrum, as in the spectral library. And these are examples of what that Magma integration returns. So we see that a fragment of 136 is correctly assigned to the atomic part of the substructure of the molecule. And in particular, some losses, like 162, I think many people working with plants or natural products would immediately think of sugar. So that is quite clear. But the other losses are actually pretty hard sometimes to find. Like, what is it exactly what this loss 60 is standing for? And this kind of automated annotation really helps there. Humans are better in finding fragments than in losses. At least that's my experience as a human being. And also, what is interesting is that sometimes a loss actually represents different substructures, because of course we have isomery in mass spectrometry. So even though we now know which atoms are in this loss, they can be configured in a different way. And we get an idea from this kind of spectral library-based analysis of how many different isomers there are. So annotation is still an issue. I mean, if you make the molecules a bit smaller into their substructures, it will come a little bit easier sometimes, but still, it would be nice not to reinvent the wheel, right? So we came up with MotifDB as well, a database of almost detectable master motif substructures. So input to start it up were a lot of spectra from beer, from urine, I will show you in a minute, and then from the GPS and mass bank. You get a lot of motifs, and this is a motif for material data set that I analyzed. And then with the help of literature and expert knowledge, I could assign this particular motif to the lactone ring of this actinomycin D molecule produced by bacteria. And now it's part of this strepsalini motif set in MotifDB. So if you have bacterial data, you know that there are Streptomyces Salinospora in, and you add this motif set, and there are actinomycin molecules in there, you're very likely to get that motif assigned to them, and you already know that these are likely to be actinomycin-related molecules. So now next time, we can add the relevant motif sets for each experiment, think about context. We've heard it more often. It doesn't make sense to add urine motives to your planned data set, all right? So take the motive sets, take the database that is relevant for the context of your experiment, and then you can still add 3 motives to kind of find the not yet discovered chemistry. Yeah? So since there's a focus on clinical applications this week, I also show some examples of urine analysis that was also published during my postdoc time. And I analyzed quite some urine LC-MS data files, and you can see examples of substructures that I could annotate. I will leave it up to you to see if that makes sense to you, but to me it made quite some things you would expect. But some examples, because this data came from a collaborator who was a clinician, and he dealt with patients with hypertension. So I was particularly also interested in drug screening capacities. If you're interested in that, there's another paper, I think 1 or 2 years earlier, on molecular networking and drug screening in the same data set. And this is an example of a motive that I could connect to losartan, or actually all sartan-based drugs. So that part of the structure is very well visible in positive ionization mode. And all these fragments here are present all the time in any of these drug metabolites. So again, if you add this to your urine data and you know you can expect some drug-based molecules, then yeah, you will probably see if losartan or another sartan drug is present. And then we could also do some comparative analysis to see, do we see difference between urines, like in presence, absence of this motive. And another example is here. This is another drug for rapamycin, and here we actually see that we both have fragments, but also losses, right? So actually, in some cases, a neutral loss is also included in the master motive feature set, as it is likely to be commonly seen in in this particular substructure. Then we also have some food-derived molecules, master motives, and corresponding metabolites. So I could find a motive for protein betaine-related structures, and also one for citric acid-related molecules. And I wanted to point out that these are only losses, actually. So, so we have a series of losses that is then representative for this kind of structure that you can actually connect to the intake of citrus fruit, hence the name citric acid. Sometimes life is easy, right? And then you can also see that the presence of this motive and the associated metabolites can be quite different between urines, indicating that some voluntary patient did have something related to citric acid or citrus fruit consumed prior to sampling, and others not. You've seen molecular networking, and I think it's a great tool, so keep using it. But it does have limitations, as most things in life. And that comes when we have these two clear substructures that both kind of clear peak present, then if we force some grouping, so family formation, then the tool has to choose. Do we put it in the one or in the other? And here we have an example of this molecule that contains both ferulic acid and the ethyl-phenol substructures. And in the end, we see that it ends up in only one of the molecular families. However, if we would use master motives and assign also them, then we can still see that both substances are present. And actually, for the example data that you have and the drug that you search, did anyone already look at the spectrum of this drug that you are interested in? No? Who did? Did anybody find it? Ah, Robin did. Good. Did anybody try to look for it? Ah, did anybody try to look for it in the molecular network? Not yet. Ah, maybe it's a good to see if you can find a family there. But yeah, I can spoil the beans a little bit. Yeah, don't search too long for it because you will unlikely find it. And the reason is that that's another limitation of molecular networking, is that it's not only the similarity scoring we're using, but also a lot of filtering. For example, the two spectra need to share at least 4 or even 6 fragments. But what happens if your molecule only has like 1 or maybe 2 clear fragments that we can compare? Well, then of course we will not be able to connect them in a network. And MS2LDA doesn't have that restriction. So some motifs will be really based on 1 or maybe 1.1 clear fragments or losses. And in that case, we can still group things based on that. We will see that soon. So together with Madeleine, who I think will be presenting tomorrow again, and Kyobin Kang, we then developed Model Enhancer to combine the results of MS2LDA and GPS, molecular networking, to get to kind of chemical details of molecular families. And I will show you an example of that plant-based study. So we have the molecular network. All the colors are different chemical classes. So first we could say that, okay, the chemical classification by Model Enhancer made sense. We have all these different plant-related classifications. If you're more interested in Model Enhancer, please feel free to come by later to me or tomorrow, Madeleine, to ask questions. And there's more people in the room that I think have used it before. But now I want to focus on this MS2LDA integration. And what we can see is that this is a family of flavonoids, flavonoids. They are really widely abundant in nature and plants. So not that it's surprising to find them. However, it's one family. But now if we put on the motif information, then we see that the top has blue motifs inside, and the bottom has the light blue purple motifs inside. And actually we can see that this is not like one family. You know, actually it contains 2 subfamilies of camphorol and quercetin related molecules. And during my PhD, I started to analyze tomato data, and the first LCMS file that I really went into detail, I think it took me like 2 or 3 months to analyze all the spectra and see, okay, is it quercetin related? Is it camphorol related? Is it quercetin related? Da-di-da-di-da. And now, yeah, running this in, let's say, 2 days, 1.5 day, the answers are right in front of me. So actually, of course, it will take some time to set up the methods, to kind of get to know them, get a feeling for what they're doing. But then they will very likely save you a lot of time. And you will not spend like months on the analysis of one file only, one. So typically nowadays we run 50 or 100 or 200 files. So another example is this triterpenoid family, where we can actually see that different organic acid molecules are conjugated to this triterpenoid backbone, protocategory acid, phenolic acid, comuric acid, and you get a really quick overview of their presence and occurrence in this molecular family. So all very nice, yeah. But how do we use it? So I already said I would definitely recommend to use the GPS-based workflow because everything will already be integrated and you don't need to do a lot of additional steps to make it all work together. And 2, because there's a button, right? Analyze with MS2LDA. So you push the button and you arrive at the workflow, and all the files that you need are already there. Yeah, so that is the good news. And this is actually the job that Scott run for the summer school, example data. And then you end up here. So you get your reanalysis of this particular job ID of what you run before. And then all the files you need are already correctly placed here. So, but what we still need to do is kind of define what kind of settings we need. And that is something that I wanted to make sure that you at least get an idea of how to approach that. Well, first of all, this is what you see in the part with the settings. So you see that the motive DB selection, all the motive sets that are present here are by default included, and the other fields are not shown yet. So let us start by kind of making sure that we see everything, and then we start above, and then we move downward. So, well, first of all, this advanced MS2LDA parameters, yeah, I mean, maybe I wouldn't call them advanced, but basic MS2LDA parameters. But okay, that's a different story. Make sure that you know your data. That is basically my main message. So what I typically do is actually I open the MGF file and I just look at spectra. So that's also what I did for the summer school sample data. I opened it to see, okay, we have fragments, we have intensities. How high are they? I mean, can I see the noise level in this MGF file? Because it's this MGF file coming out of the feature-based molecular network that we put into the tool, right? And there's one thing to understand: the more features we put in, the longer it will take, and the more you have to analyze. So there's a balance there. Of course, you can squeeze out a lot, and then there's nothing or hardly anything to analyze. But if you input a lot of noise, it will just, you know, unnecessarily delay your outcomes. So based on that, then I assign the noise level, and that will be different for all of you. So for this particular example, I chose a setting, but yeah, my main message is go there and look. 80 to 90% of the errors, jobs that I get contacted about is because people wiped out all the fragments in the data. So then they end up with an empty file that they feed into the tool, and then the tool is not happy. Yeah. So, and then they said, yeah, they contact me and I said, yeah, well, maybe check your minimum noise level setting. Yeah. So the settings here are default, but they don't mean that they're good for your data set. Yeah. In this case, they're default for an LCMS, MS data file, run on a Q executive, etc., etc. And maybe your data is from the top. And maybe you don't want to have a very accurate bin width. So I heard before that some people, weren't really familiar with the concept of binning. But binning means that if you have all the fragments, you can see them here. Yeah. How do we know if this fragment here, 231.1.224, is the same as the 231.1225 in another spectrum, right? So we have to somehow find a way to do that. And one way to do that, I'm not saying it's the best way, but one way to do that is binning. So simply we start at 100, and then we put together all the masses between 100 and 100, let's say, .1. And then all the masses between 100.1 and 100.2. Well, you got the idea now, right? I will not continue till 1000, but that's what happens in the tool. And that is what we call binning. So the smaller we put the bin width, the more bins we get, the more features, the longer it will all take. That is the kind of the bottom line. Then the number of iterations, I think you can, that one you don't really need to touch. 1000 has been proven quite okay so far. Minimum intensity I already discussed at length. And the free motives, yeah, that is not easy, because actually you have to guesstimate how many substructures are in your data, and that is of course a very hard job. So, but the good news is if you are a little bit above, or even a little bit above, that's okay. If you're going mega above, then you may get some interesting results. And of course, if you choose way too little, the same thing, because things will be put together that shouldn't be. So yeah, if you have a large data set, to start with 250 or 303 motives and add the relevant motive DB kind of annotated motive sets is a good starting point, I think. Then the motive sets, I think I already gave it away a little bit with my focus on context, but Yeah, by default, they're all included, but don't do that. I mean, really assess which ones are relevant for your data set. Okay, if you have like a urine data set, you may want to include GPS, mass bank, and urine. Yeah, if you have a positive mode data set in plants, then you may want to include GPS and mass bank, but not the others. Here, I'm not a robot, but what happened? Are we back? Yeah. For example, the Remnasia plant, the motive set is in negative mode. Yeah. So if you have positive mode data, it doesn't make sense to include that one. So etc. etc. So check what makes sense, include those to help you on the way, and then there are more motive sets on the Motive2B website, and you can then if choose to add them as well. But I would recommend not to start immediately with that. And then these are the advanced parameters for the output, the combined output of GPS, molecular networking, and MS2LDA. And if you just start with it, just leave it at the default value. All right, that's okay. So this is what I came up with for our data set. So I chose a bit of 0.01 to kind of not unnecessarily make the analysis too long. The minimum intensity of 1000 and the free mode is 150. It's just a starting point. Also because we do include in total 200 motives from Motive2B, which is already quite a lot. Yeah. And then the results look like this. When it finished, this one took like nearly 5 hours on the supercluster in San Diego, and it gives you a number of things to look at. So I'm not going to go in detail about all of them today, but we can look at the view pairs with the motive edges. That is the third one on the right hand side at the top, and then we see actually the cluster ID, the feature ID, another feature ID where it is connected to, and then the type of interaction. And we can see now that we have a lot of motive. We have coaching-based interactions, which you know from the molecular networking, but now we have also motive-based interactions. And we can see that some motives only have a number, and other have like a GPS motive, urine motive. And as you may have already guessed, the ones with a name and number, they come from Motive2B. The one with only a number are the free motives that are included, right? Then we can also look at individual motive details. And there, for each spectrum, for each feature ID, they are listed here. But you can see that some of them are also present more than one. And that means that they have more than one motive assigned. Yeah? And then we see that for all the motive sets for Motive2B, there's a direct link to the motive in Motive2B. So you can check it out and see if you agree with it or not. And also the annotation is there. So you can actually already search if you are particularly interested in a substructure that you know is in Motive2B, then you can put the text in the search field and you can search for it. I did that because I was interested to see, do we have any diphenyl related spectra in the data? Because the drug that we are interested in has a very clear diphenyl substructure. And actually we can see that 13 of all the more than 6,000 spectra have this diphenyl substructure associated with in Motive2B. So then I went to look at all the recursion masses, and I read the paper, or I checked the paper and the results, and I compared the masses. And actually, I was happy to see that many of the masses here were actually also discussed in the paper. It means that somehow using an annotated motif from MotiveDB, I could actually pull out a lot of drug-related features. There were some masters not mentioned in the paper, and what I did, and that is also interesting because you heard about MAST from Ming yesterday. So I thought, okay, let me see if this is a biological signal or let me see if this is a biological signal or something real. And so I searched for this spectra in MAST in all the data, and actually only this data set that we used came back. So that means that it's very likely to be noise or maybe co-fragmentation with a real metabolite, or well, not something biological, I would say. So in the end, I could see that most features here in this list are indeed drug related, and some of them are isotopes or probably co-eluted masses with real drug metabolites. So another thing, what is nice, is that you can directly download the cytochrome file just to get an ID, or sorry, view in the browser to get an idea of whether motifs are actually assigned. I would actually only use it for that, and I wouldn't download this cytoscape file. Why? Because if you just download directly from GMPS, like from the regular way, you get a bit more freedom in how you color the edges and how you define the nodes, or at least it was easier for me to get it to work. But this is a good first screen where to see and if anything happened, because all the colored lines here are motif interactions, all right? And this is one that I created myself from the combined cytoscape data that basically is empowered by Molten Enhancer. And then I think it is nice to show you that you can use for annotation, for grouping, but also to assess whether a molecular family is one molecular family, or maybe it consists of two subparts, as we already see. And then on the left-hand side here, you actually see that the top features, they share all one particular motif, but that is not shared by all the features here. So that can make you wonder whether the connection between 229 and 199 should be there or not. And of course, it's all procedural. It's all kind of trying to organize a large data set. So some connections will be correct and others will be incorrect. And this is one way of assessing that, right? And on the right-hand side, you see that they share a lot of things, including some MotiveDB motifs, so that if you are interested in one of those features, then you can also start to look into more detail about that. But what we already also see is that this family consists of a lot of the same masses, right? So a lot of the same precursor masses. And yeah, one thing, of course, if your data has a lot of the same molecules fragmented a couple of times, those are also patterns that MS2LDA loves, right? Because, you know, it's the same thing fragmented a couple of times, same spectra, so it will immediately jump on it and create a motif for it. Not what you probably are interested in, but it happens. So, of course, the quality of the motifs is also dependent on the quality of the data. And one way to check that is to see if the motif actually consists of different precursor masses or parent masses, right? I mean, if there are different masses around and they all share the same motif, that for me is already a good sign. What's also nice to know is that Ming introduced GPS2.org yesterday, and together with Alberto and others, the GPS MS2LDA workflow should be usable in GPS2.org. So if you start to switch to a new platform, then MS2LDA should be there. And MS2 Query is being built into as we speak. So I hope that will be available also in the nearby future to use from GMPS2.org. So in the remaining time, if my laptop allows, I will, and MS2LDA.org allows me, I will briefly show you a little bit of how to navigate once you have like a data set and you want to know more in detail how the motifs look like. and which steps to take. And basically, if you upload your LDA dictionary file, so there's one option in the results file that says download MS2LDA dictionary. So you download that, you have a .dict file that you upload in MS2LDA.org to the upload screen. And then the first thing to do once it's finished, because it will take time, it will take maybe an hour, half an hour, depending on how busy the server is and how big your dictionary file is. And then once it's done, you can go to the experiment options, and I will show that again. And then you can first set the probability and overlap score thresholds. And why I mentioned that is because by default, they're all very low. And that means that a lot of spectra are connected to motives, which is nice, but there's also a lot of false positives. So we want to exclude them. So the probability I typically set at 0.1, maybe 0.2, depending on the data set. You can play with that as well. And the overlap score is something that I haven't mentioned yet. So that is also to kind of avoid one. So there's one drawback of LDA, the topic modeling, is that each spectrum has to go somewhere. So say that you have one molecule that is very different from everything else. Yeah, of course, it has also a fragmentation spectrum, and it has different fragments than everything else. Then normally you would say, okay, let's forget about it, right? Let's just not put it into a motive. But yeah, LDA has to do it. So typically this ends up in a random motive, not sharing a lot of its features with the motive features. So this overlap score, if you put it on 0.3, for example, it will remove all those false positives from the motives. Yeah, and then the rest of these things I will aim to show you by looking into the files. And this is the final slide, and you already saw it, so I can thank you for your attention. But let's first move to stop share to the right. Yeah. Okay, and then share it again. Hope this works like this. Do we see it on Zoom? Okay. So this is what you arrive in the summary page, but let's first go to the website. So this is if you go to the website, it still works. Thank you guys for cooperating. So you see this. You can register for a login account. However, you don't need it to look at public data. And all the results that I made public. So in principle, you should be able to reach them for the different for the two groups and also for the example data. And then here we have experiments. Well, that usually takes some time to open. And then when you would come with your GPS data, your dictionary, you go to create experiment. And then rather than create, we go to upload because we already have run it. And then you give a name and a description. I'll leave that up to you. Make it informative for yourself so you later on remember what you actually put in. That's my tip. And then you include the bidding size here. Yeah. So which bidding you used in GPS MS2LDA. In our case, it was 0.01. And then here you choose the file, the dictionary file. And then you push upload. And then it will upload. Well, but it's good to show, right? And that's the screen you should get. And then the dictionary file from GPS MS2LDA. So I don't know, do I have it? So here it's download MS2LDA dictionary, right? So if you download that, the dictionary file is in your downloaded folder. All right? Yep. No worries. And then you will see it here listed in the pending experiments when it's uploading. So this is obviously a failed one, but it's there. So I can show you that you see that pending experiments. And here are the ready examples. So if you click on it, you will typically see this, right? So we don't click, it's empty. We click on it, it opens up and it has all these options. And I already told you, the first thing to go to is to this experiment options. And then you add a new option. And then we have to be patient a little bit. And then you start with the overlap threshold. You give a number, let's say 0.1. And then you add, and then we can go to the overlap threshold. And then we put 0.3, for example. Yeah? And then once we did that, it's important you go back to experiment. It also means that the new settings will be added on the background. And then once it's reopened, and I think more people are opening the website now. I can see that it's taking a bit more time now. Then it will reappear. But that's why I already had it open, because once it's loaded in your browser, we should be good. So when we will see it again with all the options, see, then you will see one is called summary page, and that's what I opened here. And this is also the one that you can make public. So if you want to share your experiment with a paper, you can do that here. And then once it's public, you can share the link and everybody can look at it. But by default, it's private. So you are the one to look into it. So all the things, blah, blah, blah. I just want to highlight, we have all the fragmentation spectra details. So we can see the number corresponds to what we expected, 6,000 and a bit more. And all the precursion masses. We have the motive details. So we have in total 361 motives, composing of 153 motives and the motives from the motive sets. And here we have all the various features. So they are a bit selected because they have to be in at least one master motive with a probability higher than 0.05. So it's not all the features, but it's like those that are more likely to be relevant. So if you know of a fragment that is important for your research, then you can start to type it in and it may or may not appear, right? So here we see if you would be interested in the fragment 150 0.350, yeah, you can see in which motives it's found, and also for the loss that is also selected for the same value. And here we have all the details. So have feature ID, or row ID, the document ID, and then the motive, probability, overlap score, etc. And from this kind of things, you can download a CSV file if you wish to do so. So each of these tables has the search option and the CSV option. Sorry, I think we are, yeah. All right, so now I can show you that it's this page. I will not open it again. This page takes time because it has to read in all of these things. If you're interested in only the motives as a first thing, then you can also go into the show master motives page. Yeah? What else? So here we can already also look for die for new, right? And then we see indeed, and that corresponds, of course, with the GPS MS2LDA view, that we have 13 spectra associated with this motive. So for annotated motives, we still need to check, of course. You need to check whether you think this spectral associations make sense, but at least there is already an annotation and you have an idea that this motive could be relevant. But for so-called free motives, and I opened a random one here, that's not the case. So typically you can look at the fragment, the losses that are found, the probability is kind of a mixture between intensity and occurrence of the fragment or loss. So the higher the more likely it is well visible and or co-occurring in a lot of associated spectra. And it goes down and down and down till pretty low values. Another interesting plot is this frequency plot, where we have the various fragments and losses, similar as above, the total number of spectra in the motive, and then the occurrence. So this gives you an idea whether or not a pattern is very strong, or maybe not so strong as you would hope for. You see that one fragment is present in all the spectra, but then the second one is present in only half. So that gives you already a sign that or this fragment 141 is very unique and special. I can use it to annotate a complete substructure, or maybe you can actually say something about 12 spectra out of the 24. And then here we see all the precursor masses and parent masses. And as I already told you, you are dependent on the quality of the data. So if molecules are fragmented a couple of times, then you will see the same precursor masses, and that is also, of course, for pattern finding tools like MS2LDA, a joy, because they will immediately make a pattern out of it. And here we see that in some cases we do have this repetition, but overall we also see some different different precursor masses. And finally, actually, you can also cycle through each of the spectra and check if you agree with that it's an interesting fragmental pattern or not. Yeah? I mean, I cannot speak for your data, and I also don't have a full knowledge of this data set, but you may be able to do it for a few motives now or later if you wish to do so, or for your own data where you do have the context to see if it makes sense. Other motive, and here we see that it's also a free motive. You see one fragment, this 62, that's present in slightly more than 20 spectra, and they all have a different precursor mass, or most. I have no idea what it is, but at least it looks interesting because it's quite a strong and unique fragment. You can see it, for example, here, right? In the red here. So, no idea what it is, but I just wanted to point out that even though it's only one fragment, it can still be of interest. If it's unique and clearly abundant, clearly present, then it may be of interest for you. And this is another example, which I would say a bit more kind of strong pattern, where a lot of fragments are present in the majority of the spectra of the motive. So that is how I would approach it, to see which motives make sense to annotate. Of course, one other way is if you know of interesting parent ions, then you can first search them, see which motives they contain, and then see if you can actually solve those motives, annotate those motives. And then I think I have it opened somewhere, the motive for the diphenols. Here I have a motive from motive DB, the loss of carboxylic acid group. And that is, present in all the spectra, slightly more than 60, indicating that they contain a free carboxylic acid group. And when we cycle through the spectra, we see that some of them are really clear, right? They only have one fragmentation peak and the loss, and others do have some other fragments as well. And then, here we have finally the diphenyl substructure. So we have a fragment of 176, and I encourage you to look at the paper and maybe use MedSMS to check the plot or an MS to see how the spectrum actually looks like of the drug and of the drug metabolites. We see a fragment on 152, etc., etc. But the main, because the probability is very high, is this fragment on 176. And when we look at the future frequencies, we see that is present in all the spectra, and then some others are present in slightly less than half. Now, then here we have all the precursor masses. Again, we see a difference in masses, so that is encouraging. High probabilities, also very decent overlap scores. And here you can cycle through it. And there we actually see, we already can see example spectrum, and you see that this peak of 176 is indeed present, very dominant, and we hardly see other things. And that is, of course, very challenging for any tools that use number of fragments as overlap as one way of connecting molecules. Because if we would put it down to one, a minimum of one, then there's a chance that a gigantic hairball will exist or form. And therefore, tools like MS2LDA can be complementary to molecular network. So you can see, you can cycle through, and you can also do that for your own group data. So given time, I suggest that I'll round it off here. So I thank you a lot for your attention, and I'm open for questions. Don't be shy. It's fine. Yep. Well, to view things, so the main bottleneck is when you, let's say, press on summary page, then it needs to interact a lot with the web server to retrieve the information. But once it's in my browser, as you see now, it reacts very quickly because information is already in my browser. So it's that moment when you would go with the 10 of you and at the same time retrieve the information, I think it will die. But if you do it a little bit spread, like in the coming hour and then tomorrow, then it will survive. Yeah. And if one person, because you can still use it also to run it on a file, let's say MGF file or an LCMS file. Yeah, if that runs, then of course some of the bandwidth is taken up by that computations, and then viewing results is also a bit slower. No. Scott.
There's some compound classes you think one should be more careful generating the for highly aromatic compounds, or should there be some criteria for searching through the spectrum anyway before creating motifs, or what's your opinion?
Well, hard to say for all motives, but I have here so I have here an example of acylcarnitine related motif that I annotated myself in this urine data set that I showed in my talk. It has fragment 85 as one of the key fragments and a loss of 161. And actually you see here in the frequency that in this particular data set that you're using, that we have like 3 spectra that have this fragment and 2 have the loss. And I'm showing this because fragment 85, that particular fragment, can also come from a sugary compound, right? So when you have to deal with fragments that have a lot of different isomeric options and that are actually also present at the same time in the data, you have to be a bit more careful. But for example, you've seen the example of the diphenyl substructure, and I asked the experts, and they said that it was very druggy in terms of that, you know, we shouldn't expect that too much in nature. So, and there you see that it works, even though we only have 1 fragment. Yeah, it still can pull out interesting features for you. The same is true for like chlorinated benzyl chlorinated chlorobenzenyl substructure. It is quite unique, and also you don't find it too often in nature. So yeah, it's a combination of factors that contribute to how well it will work in practice. More questions? Can you read it out for me? Well, if you can deconvolute the DIA measurements very well, then in principle, yes. I think the bottleneck is not so much DIA itself, it's more like how we can extract the necessary information. We use both fragment and neutral losses because I think the neutral loss do add something to it. But of course, yeah, if you cannot deconvolute the data well enough, then you end up with spectra that can be yeah, not clean enough to actually do something with. So yeah, I would as input use still DDA. And I think the modern the most modern mass spectrometers are also pretty fast and pretty good in obtaining a lot of MSMS spectra using DDA. Any more questions? You? Yeah? No? Then I have a final question for you. So who of you after this talk thinks, could be of interest for my project? Oh, well, thanks. Nice. Oh, it's nice to see some hands, and I hope that the others may or may not be convinced by neighbors or seeing the results of your colleagues here in the workshop. All right. Thank you again.